Today, we will be solving the following problem in which we have to prove that the closure of A union the closure of B is equals to the closure of A union B. To prove this, we will be using the following lemma, which states that A prime union B prime is equals to A union B prime. To prove this lemma, we will first prove that A prime union B prime is a subset of A union B prime. To do this, let X be an element of A prime. Now, by the definition of limit point, we know that for any open set containing X, there exists an element from A which is unique from X in the open set. Now, since we know that there exists an element from A unique from X in the open set, we can also say that there exists an element from A union B unique from X in the open set. And thus, by definition of limit point, X is an element of A union B prime, and X is a limit point of A union B prime. Now, using the same logic, let Y be an element of B prime. Then for any open set containing Y, there exists an element from B unique from Y in the open set. And since there exists an element from B, we can also say there exists an element from A union B unique from Y in the open set. And therefore, by definition of the limit point, we know that Y is also an element of A union B, or Y is also a limit point of A union B. Thus, we know that any element in this is also an element of this. However, we want to prove that A prime union B prime is equals to the to A union B prime. So to do that, we also have to show that all the elements in this are also elements in this. To do that, let's suppose that we want to show that X is an element of A union B prime. Now, we want to show that if this is the case, then either X is an element of A prime or X is an element of B prime. However, for sake of contradiction, let's suppose that X is not an element of A prime and X is not an element of B prime. Now, if we assume that X is an element of A union B prime, then by definition of limit point, any open set containing X must have an element different from X from A union B. So now let's use our assumption over here, and since we're stating that X is not an element of A prime, there exists an open set UA which contains X. However, it does not contain another element from A. So it's an open set that has X but nothing else from A. And similarly, since we also stated that X is not an element of B prime, there exists an open set UB containing X that does not contain an other element from B. So that's an open set that has X but nothing else from B. Let's try to visualize this. So let's say that this is A and this is B, and in the middle between them somewhere is X. Now, notice how we said that X is not a limit point of A. That's why X is not over here, and it's not a limit point of B. That's why it's not over here. However, since it's not a limit point, there also exists an open set UA. So let's define that. So let's just say that this open set right here. This is an open set. It contains X, but it doesn't contain any element from A. And as you said, that's why X is not a limit point of A. And then let's make an other open set which contains X but does not contain anything from B, and this is UB. Now this satisfies what we stated earlier. However, if we notice right here, the intersection between UA and UB is an open set that contains X, but it does not contain anything from A or anything from B. However, this is a contradiction because we stated that X is an element of A union B prime, and therefore by definition of the limit point, any open set containing X must have an element different from X from A union B. Since it doesn't have anything from A or from B, it does not have anything from A union B. Therefore, we have contradiction. And since we have this contradiction, we know that this can't be true. And we know that for any X in A union B, either X must be an element of A prime or X must be an element of B prime. Therefore, A union B prime is a subset of A prime union B prime. And that's because any element in this must also be an element in this. Now, since we showed earlier that any element in this must also be an element in this, and we showed that any element in this must also be an element in this, we have basically shown that the two are equal. And we have proved our lemma that A prime union B prime is equals to A union B prime. So now that we've proved our lemma, let's use this lemma to prove our original question, which states that closure of A union closure of B is equals to closure of A union B. To do this, we will be using the definition of closure to define closure of A as the union of A and the limit points of A, or A prime, and the closure of B is equals to B union the closure or B union the limit point of B. Now, when we write this out, we get closure of A union closure of B is equals to A union A prime union B union B prime. Now we can distribute this further, and we can write this as A union B union A prime union B prime. Now, we are going to use our lemma that we proved right here, that A prime union B prime is equals to A union B prime, right here. So we can write this as A union B union A union B prime. And as you'll notice, this is a set union the limit points of that set, and that is the very definition of closure, as we stated right here. So using that lemma, we have basically proved that the closure of A union the closure of B is equals to the closure of A union B. And we are done with our proof.